We're now going to introduce analysis of variance, commonly known as ANOVA. It's a method of testing differences between groups when you have more than two levels of an independent variable. Recall that the t-tests require that you have only two levels of an independent variable. Here are some illustrations that relate to t-tests and analysis of variance. Here's the t-test with two levels. If you have three levels of one independent variable, x, you would conduct an analysis of variance,
called a one-way ANOVA.
In this example, we have more than two levels. You could have any number of levels of an independent variable.
And it's still called a one-way ANOVA because there is only one independent variable.
Here's an example, one independent variable with three levels, a, b, and c. You might ask yourself, why wouldn't you do multiple t-tests? Let's compare a with b, a with c, and b with c.
The problem with that is that you end up with an increased type 1 probability, and you're more likely to find a significant difference that is not there.
What you do with ANOVA is you partition the variance. Remember, variance is simply a measure of dispersion. We're going to partition the variance in scores, and we'll partition it into two sources. That source that's associated with differences between levels, or group means, and that variation that's within each cell or each level of the independent variable.
Our hypotheses are going to be as follows. The null hypothesis is that mean 1 is equal to mean 2, which is equal to mean 3 in our case. The alternative hypothesis is that the means are not equal.
Essentially, the alternative hypothesis says the differences between means is more than chance.
Now, like the independent and dependent t-test, one-way ANOVA has assumptions which are the same for the independent t-test. The assumptions here are normality, homogeneity of variance, continuous measurement, and independent observations, meaning there are different people in each level of the independent variable.
Importantly, analysis of variance is robust to many of these assumptions. One that becomes most important to us in this chapter and in the next chapter is the independence of observations. There'll be a great deal more about that in chapter 10.
When we get to the end of an analysis of variance, we are going to have an ANOVA source table. It starts with the source of the variation on the left, sums of squares, followed by degrees of freedom, followed by mean squares, and finally something called the F ratio.
The sources of variation are those between groups, that within groups, and the total variation in the sample. Importantly, if you think about these things, they have a relationship to the calculation of a variance. That is, you have a sum of squares and you divide it by some number and you come up with a variance. We'll do essentially the same thing with analysis of variance.
So we will calculate a sum of squares for between, and then we'll calculate a sum of squares for within.
We'll have degrees of freedom. The degrees of freedom between groups is the number of groups, k, minus 1.
The degrees of freedom for within groups is the total number of subjects minus the number of levels of the independent variable.
And the total degrees of freedom are the total number of subjects minus 1.
Now the mean squares are going to be the sum of squares and dividing it by its degrees of freedom. So the sum of squares for between divided by the degrees of freedom for between, and the sum of squares for within divided by the degrees of freedom for within.
Think back a long time ago to early in your text where you calculated the standard deviation and the variance. You had the sum of squares divided by the sample size. Well, that's essentially the same thing here. Notice we have the sum of squares divided by its degrees of freedom, and we come up with an estimate of the mean square. The mean square is a variance.
In fact, the mean squares in analysis of variance are estimates of the population variance. Both of these, the mean square for between and the mean square for within, if the null hypothesis is true, are both estimates of the same parameter, the population variance.
And lastly, you calculate an F ratio. The F ratio is the test statistic. It's analogous to the T ratio that we used with the t-test. And an F ratio is simply the mean square between divided by the mean square within. And if the null hypothesis is true, then the F ratio is expected to be 1.
Because they're both estimating the same parameter, the population variance.
However, if the null hypothesis is not true, that is, there are differences between the means, then the F ratio is expected to be greater than 1, because the mean square between the groups then is a larger estimate of the variation than is the mean square within the groups. And that gives you a larger F value. Larger F values, just like larger T values, are in the extremes of the distribution and result in rejecting the null hypothesis.
How much larger does F have to be than 1? Well, that's why there's an F table that we'll look up in the appendix. You have to go into the F table with the degrees of freedom for between groups and the degrees of freedom for within groups.
Let's use an example. We'll provide the results of this example, and then we'll go to SPSS and actually calculate this so you can see how we did so. In our case, we're going to do a one-way analysis of variance. We have 4 levels, A, B, C, D, and the 4 levels are differentiated in this way. The independent variable, A, people get a pedometer only. B, they get a pedometer and written support to be physically active. C, they get a pedometer and personal support. And D, they get a pedometer, personal support, and computer support. So in some fashion, as you move from A through D, there is more and more support in order for you to be physically active. The dependent variable then is number of steps taken per week. The concept being is if we give you a pedometer and additional encouragement, you're more likely to be physically active. So we think that there is a relationship between X, how much support you have to be physically active, and whether or not you are physically active based upon the number of steps recorded per week.
Now remember, we have a null hypothesis and an alternative hypothesis. The means are equal or the means are not equal.
Here's the basic setup for our study. We have 4 groups. We have 50 people in each of the groups. Notice the sums of squares are between. Look at the degrees of freedom. How did we calculate them? For between groups, it's the number of groups minus 1, so 4 minus 1 is 3. Within groups, it's the total number of observations minus the number of groups, so that's 200 minus 4, which is 196. And then the total degrees of freedom is the total n, 200 minus 1, is 199.
Notice that the degrees of freedom for between groups and the degrees of freedom for within groups add up to the total degrees of freedom. We are partitioning the degrees of freedom just like we're partitioning the variance.
So we would run this with SPSS one-way ANOVA. So here are our results. You'll notice we have 4 groups with 50 people in each group. And you can see the mean steps per week for the 4 groups, starting with 31,420 and increasing up to 50,660. Well, are those means significantly different from one another, or are the differences between those 4 means simply due to chance?
Or sampling error.
Here's the ANOVA results. Notice we now have in here our degrees of freedom. We also have in here now the sum of squares, the mean squares, the F, and the significance or probability. So when you look at analysis of variance, the key thing to look at here is the F and the significance level. The F is 15.049, which suggests that the differences between these 4 means is not due to chance. So you reject HO at a probability of less than 0.001. It's very unlikely that the deviations amongst these 4 means is a result of chance. There's something going on here. There's a relationship between X, how much support they had, and Y, how many steps they took per week. We'll next turn to illustrating how we got these results with SPSS.
Here's our data set for our SPSS example. In the first column, we have the group membership, 1 through 4. In the second column, we have steps taken per week.
So if we were to look at the variable view and the values for group, you'll notice that 1 is pedometer only, 2 is pedometer and written support, 3 is pedometer and personal support, and 4 are pedometer, personal support, and computer. So to run a one-way analysis of variance, we go to Analyze, Compare Means, One-Way ANOVA. Up comes the One-Way ANOVA window. Group is our factor. Steps is our dependent variable. Options that we would choose would be descriptive statistics, then continue, and OK. And here you see the results just like you saw in the previous slide. We have a few extra things about the 95% confidence level and so forth, but here are the results for descriptive statistics, and here's our analysis of variance result. Very simple to run analysis of variance. Know what the independent variable is, how many levels there are, know what the dependent variable is. Once you've found a difference, you might be wondering, where is this difference? We notice that there are differences amongst these 4 groups, but where is that difference? That's where we'll turn in the next video.